Hello everyone, today we're going to talk about cardinality. Before we start, make sure you understand injective, surjective, and bijective. If you don't understand those three terms, you cannot survive this chapter. Also, if you're a math student, you might know that I really like this chapter. That's why I prepared a lot of material, as you can see here. Bear in mind that a lot of material, not a lot, some material I'm going to cover today are beyond the scope of this course, which means even if you don't understand what's going on, that's okay. I'm just introducing those to you so that you know more technique, more method you can use during your exam if you get stuck. But if you don't understand, that's okay. Everything in purple here are the materials that you should know, but there are two questions here, number 2 and number 3 here. I wrote them in blue because you don't need to know them. Okay, anyway, let's start. First of all, definition. Two sets A and B are said to have the same cardinality if there is a bijection between them. The term cardinality here, this just means the size of the set. What does that mean? This means the number of elements of a set. Okay? For example, we have a set A that contains 1, 2, 3. Then the cardinality we denote by this, which looks like the absolute value. The cardinality of set A would be 3 because you have 3 elements here. Well, some of you might ask, what about empty set? We know that the empty set is the subset of any set, would be a subset of A, but bear in mind here, when we talk about cardinality, we're talking about the number of elements, not the number of subsets, which means unless we have another set B that includes empty set here. Okay, I'm gonna write 1, 2, 3. Unless your set has empty set as an element, we don't count this. Well, in this case, this would be an element of B, and your cardinality of B would be 4, because you have 4 elements here. Okay? The theorem here, the set of natural numbers n and the set of rational numbers q have the same cardinality. Well, what does this mean? This means, okay, by definition here, since they have the same cardinality, you know that there exists a bijection between them. Or I should say there exists a bijective function, bijective f, that maps from natural number to rational number. I'm writing this because the proof of this theorem, okay, the proof of this theorem is really important. That is our first proof technique. I call this zigzag or snake. I'm pretty sure your professor showed the proof to you in class already. Please go over that proof. It's really important that you can use it all the time. Here is an example. I want to show the union of a countable number of countable sets is countable. Okay, this is a back example because we need to go over countable first. So let's do this first. Countable here. The definition is right here. So a set that has the same cardinality as a natural number is called a countable set. Notice that in 102, finite sets are not countable. The reason is that finite sets, they don't have the same cardinality as a natural number, that's why they are uncountable. But I'm saying 102 because if you search anywhere else, finite sets are countable. Okay? So in reality, finite sets are countable, but in 102 they want to make your life easier. We claim that finite sets are not countable. So please make sure you bear that in mind. Here, an infinite set that is not countable is called an uncountable set. So in this case, we're talking about the union of a countable number of countable sets. Okay, so we're talking about countable sets are countable, which means we need to show that the union has the same cardinality with a natural number. So here is a proof. So we have a countable collection of countable sets. S1, S2, S3, each one of those are countable sets. So they all have the same cardinality with a natural number. And each of them is countably infinite. So we can label the element of Si so this means, this whole sentence means that we can, for each S, like S1, S2, S3, for each Si, we can list them. Some of you might know that if a set is countable, it's listable. You can list each element in certain order. This is what they mean. So we can list the element of each set Si as like AI1, AI2, AI3, and we can just like list all of them just like this. Okay, so they're just telling you that you can list out the element of each set because each set is countable, and there are countably many of such sets. Well, here is when the technique comes in. The reason we call this zigzag or snake is because when we list the union of the whole set, okay, the union of this those countable sets, it's like a giant set, which is S. We denote the union as S. So to show that S is countable, we want to list all of the elements. Remember, countable means they are listable. You can list all the elements like one after another. So here it comes. We would proceed like this. So we start with A11 and we go to A12. Okay? And then we move to A21. And then to A22. And to A12, A21, A31, sorry. Now we go to A31, and then A22, A13, A14, A23, A32, A41, A42, A33, A24, A15, like this. So it's going like zigzag or snake. In this case, we know exactly, let's say like 100th digit of S would be, like the 100th element of S would be. So it's like in certain order that everyone knows the certain numbers of the element is. That is why we can say, so here, in this way we zigzag through the entire array as we did in the proof of Q. Okay, so you can list all the elements of S, which means S is countable. The second example is using the same method as we said, zigzag or snake, whichever you like. We are trying to prove the Cartesian product of natural numbers is countable. So I draw this graph. I'm not showing you a rigorous proof, but I'm just showing you the idea. So it's the same idea as here. As I said, if you can list out all the elements in certain order, such that everyone knows like 100th element or 200th element of your set, then you can show that this set is countable. So for this case, I draw the graph here. As you can see here, all those dots here, represents each of your dots in your Cartesian product. So if you think about an Cartesian product M, it's gonna be like 1 1, 1 2, 1 3, 1 4, and continue, and then you have like 2 1, 2 2, 2 3, and so on. Okay, so I draw it out just like this. So this will be a 1 1, 1 1, 1 2, 1 3, 1 4, 2 1, 2 2, 2 3, 2 4, just like this. And we use the same method to list all of them out. So we start with here, 1 1, and you can go to here, and then here, and then here, like a snake. Okay, just like this. So in this way you can list all the elements out. Not really here. This will continue go here, and it's infinitely many. Okay, so in this graph you can see that we can list all of them out, or if you like to write down all the pairs, just like what I did here, it's the same thing. So you go from here to here, then go from here and here, like this. But as you can see, it's the same thing. Okay, I'm not showing you a rigorous proof, but it's the same method, really similar to example 1. Anyway, I left 2 practices here for you. As you can see, those 2 should be like exactly the same as example 2. So I'm pretty sure you guys can do it if you understand what I just talked about. If not, please send me an email. Yeah. Anyway, let's talk about the second proof technique, which is we construct an explicit bijection. So we just construct a bijective function directly. First of all, the first 2 questions are typical cardinality questions, which is like they give you 2 intervals or union of intervals and ask you to show that the 2 sets or 2 intervals have the same cardinality. There are certain ways to do this, and my favorite way is to draw them out and think. So first of all, we know that we need to map from A to B or B to A. It doesn't really matter which way because it's a bijective function. So let's say A to B. First of all, I draw those two out already, by the way. First of all, if you observe, you can see that the length of your A is 1 and the length of your B is 2. Okay, you want to make A equal to B. You want them to look the same. So first of all, you want to make your A have the length of 2. What you can do to make its length of 2? You can times 2. Okay, so first of all, we make A has length of 2. Okay, so we times 2. So we'll get 2x. So we start with x. And you want to make it has a length of 2, so we have 2x. So after you have 2x, you'll see that your A changes from 1, 2 to 2, 4. Why? Because, well, you times 2 times 1 is 2, 2 times 2 is 4, okay? So now your new A looks like this, not including 2 and 4. So this is your new A. Well, your new A, let's call it A prime, your new A still does not look like B. They have the same length, but somehow you need to shift your A prime to your right such that they look the same, right? So you want to shift, okay, so hold on, this is 4. You want to shift your A prime to your right by 1 unit. Such that your A prime B overlap. That is why we shift to the right, which means we need to add 1 here. That is why my function will be 2x plus 1. Okay? If you want to go backwards, it is the same idea. The backwards would be, first of all, your B now has a length of 2. You want to make it 1, which means your fx, you need to divide it by 2 first, because you want to make it length 1. Okay? Now, after we divide it by 2, what do you have? You have 3 over 2, 5 over 2. Okay? And you want to make this to 1 and 2. To 1, 2. What you need to do is you need to minus 1 over 2. Because if you minus 1 over 2, you'll get 1, 2. Okay? Because, okay, this minus 1 over 2 will give you 1. This minus 1 over 2 will give you 2. It's the same idea. I hope you understand what I'm talking about right here. Notice that we can do this because both of our A and B does not include the boundary point. Okay, those are all round brackets. That's why we can do it. So make sure you're careful enough to make sure they are all round brackets or have the same structure. The second one is a little bit harder than the first one, but it should still be straightforward. So we have our A, which is from -1 to 1, including -1 and 1. And our B is a union of -2, union -1 to 1, exclude -1 and 1, union 2. Again, I draw the graph right here. As you can see, now our A and B kind of have different structure. And we want to make them look the same. To make sure we make them look the same, we want to write A in the structure that really looks like B. So we want to write A as a point union an interval, round bracket, union another point. And that is how we got this. Because we want our A and B to look the same. So in this case, we have the point -1 and 1, and then exclude -1 to 1. And this is how I came up with my function. It's a piecewise function. So I mapped -1 to -2, and this interval to itself, and 1 to 2. Okay, that's how I mapped it, and this function is obviously a bijective function. If you don't trust me, prove it yourself. Okay. Number 3 and 4, or actually C and D. Numbers C and D are another type of cardinality function. Again, you need to show A and B have the same cardinality. And before we do C and D, I know the answer is right here, but don't look at those. Look at this part. Okay? This part. Please make sure you know the graphs of the following functions. And you should be familiar with transformations from high school. Please make sure you know, because if you know the graph, it's gonna be much easier to come up with a bijective function. Okay? For example, well, if you know those 4 graphs, C and D should be easy for you. Okay, let's just forget about this first. Let's move it around. Okay, so I want to show real number and negative infinity through 3 have the same cardinality, which means I need to build a bijection between those two. For me, I always feel like starting from a bigger set to a smaller set will be easier, but some of you might think the other way around is easier. It doesn't really matter. Since it's bijection, it doesn't really matter which way you start from. But just based on this, I can somehow come up with this graph here. Okay, so I want a bijective function, and I know this is what my function gonna look like. I want something like this. Alright, so based on this, you can think, well, what kind of function that looks like this? This is what you need to think. What kind of function that looks like this? Well, usually if function has asymptotes, or this one, or this one, or this one. Okay, but it's from R, which means this one is not there. It's from R. Well, asymptote, this one has a horizontal asymptote. This one has a vertical asymptote. Oops. This one has horizontal asymptote. This one has a vertical asymptote. In this case, we need a horizontal asymptote, which means probably this is our function. Okay, so think about how do we make this function look like this. It's time to use, I don't know, high school math. Okay, anyway, I'm just gonna skip this. This is our function. So you just reflect this based on your x-axis, and move up 3 units. Okay, you should know this, by the way. If you don't, please practice. Please know the graph. Anyway, number D, I think this was a quiz question last year or the year before, but this was a quiz question, I'm pretty sure. So need to show A and B have the same cardinality. Again, you need a bijective function. Again, I'm just gonna move it over. Again, just by looking at this, you should know, you can kind of draw the graph out. You know this, your function kind of looks like this. Now you need to think, okay, so what type of function that looks like this? Well, the first thing that come to my mind is this one, but I know this one does not work because this one does not have a horizontal asymptote, and I want a horizontal asymptote, okay? And this is why we have this. The arctangent. This function is really useful in 102, especially this chapter. Make sure you know the graph. Well, I drew it out already, but make sure you know the graph. And make sure you know this is pi over 2, this is negative pi over 2. Also, for those two functions as well, make sure you know those. Anyway, if you know we have arctangent this function, you should, well, by high school math, you should know this is our function. Okay? Please, please, please practice on this type of question. Those are really important. I can't guarantee you it's gonna be on your exam, but those are important. Okay? Anyway, example 2 here is another type of cardinality function. We need to show that the set of all the integers which are divisible by 3 is countable. Here I showed you two types of proof. One is informal, the other one is formal. The informal one, okay, I'm telling you 102 accept such proof. Well, well, at least we used to accept this kind of proof. I think we still accept this kind of proof. Probably check with your coordinator, but I think they still accept this kind of proof. Although it's informal, but it's not that formal, but I think they still accept it. It's still a bijective function. And if they do, I suggest to you to use this because it's much easier than a formal proof. Sometimes it's not easy to come up with, a formula. It's much easier just to list them out, okay? Anyway, you should know that all integers that are divisible by 3 can be written as 3k, where k is an integer. Therefore, we can just list all the elements out. So we have natural number from 1, 2, 3, 4, 5, 6, 7, and we list it out in certain order. So I started with 0, and then 3 minus 3, 6 minus 6, 9 minus 9, in this order. I know some of you might want to write it in this order. So we have 0, 3, 6, 9, and you have 12, and after this you start with minus 3, minus 6, and such things. Please, please, please do not do this. Okay? Why is that? If I ask you which element, okay, which position is your minus 3 at? You have no idea because your here, okay, those are like in between 12 and minus 3, there are infinitely many of them, and you have no idea what is like your 10,000th element, okay? It's like you can't list them all in this way. So please, please, please use the order I wrote here. Well, again, this is clearly a bijection, so don't have to prove anything. The formal proof, I wrote it here as well, but I suggest you to use this, okay? Because this is much harder to come up with. I mean, it's more formal, it's still true, but it's much harder. It's gonna take you much longer time to come up with than just list them out. Anyway, we talked about the definition of countable, uncountable, and I wrote down some common countable and uncountable sets. Please go over, well, we can go over it now. First of all, natural number, because that's how we define countable sets. E stands for even number. This is even number. This is odd number. Okay, and the integer, rational, those you should know already. Also, infinite subsets of countable sets are countable. This one you should know. It can save you a lot of time if you're doing a multiple choice question. Okay. Also, we just proved at the very beginning that countable union of countable sets is countable. Well, if you don't really understand what I'm talking about, well, in 102 they really don't give you countable, like an infinitely countable union of countable sets. Usually you can just thinking about finite, okay, finite union of countable sets. So for example, natural number union, no, not a good example. Let's think. Okay, even number union odd number. Okay, this is countable, this is countable. It's a finite union of countable set. The whole thing is countable. Also the Cartesian product of countable sets. We proved this in example 2 when I proved this. Okay, you can use this proof to this. Remember, the Cartesian product of countable sets is countable. Some common uncountable sets. Well, you should know real number. This is real number minus rational number, which gives you irrational numbers. So you should know irrational numbers is uncountable. Also, the power set. The power set of countable set is uncountable. The power set of uncountable set is uncountable as well. Since I mentioned power set already, let's review it a little bit. Okay, where's power set? Here. Okay, the definition here. The power set P of x is a set of all subsets of x. Everyone should know this by now. Okay? But I'll still give you an example. Let's say your x is 1, 2, 3. Then your cardinality of x would be 3. What is the cardinality of your power set of x? Okay, everyone should know it's 2 to the power of 3. Okay, you should know this. Anyway, let's go back to here. Okay, where was I? Oh, here. The power set of countable set, the power set of uncountable set. Why is that? It's because of this. Okay, I'm going back to here. Cantor's theorem. Okay, we know that the set x and the power set of x do not have the same cardinality. Well, in fact, the cardinality of x is strictly less than the cardinality of the power set of x. Okay, this is true, which means if we take the power set of a countable set, then the cardinality of this power set will be strictly greater than the cardinality of the countable set, which means it's never gonna be countable. Anyway, let's go back. Here, we've talked about this. Another important one is intervals. Everyone should know that intervals are uncountable. Also finite sets. Again, I'm gonna put bracket here because this is true only in 102. Okay, true only in 102. Also, the Cartesian products of uncountable sets, such as our Cartesian product R. What else? Oh, another one that I will prove later. I'm not gonna spoil this, but I'll prove later. Theory, the set of real number R is uncountable. We talked about that already. I post this here because I wanna talk about this. Cantor's diagonal argument. This proof is quite important. I mean, it was rarely being tested in 102 because a lot of students, they don't understand the proof itself. So I can't guarantee it's gonna be in our exam, but I still think it's quite important and it's really interesting. I do think it's an interesting proof. So I'm not going over the proof of this theorem. You should go over that. But let's just use the argument to prove another question. So A is the set of all infinite sequence consisting A's and B's. So this means we have sequence that has like A, B, B, A, B, A, B. So this sequence has only A's and B's and it's infinite, okay? Like that. And A is a set of all such infinite sequence. And I want you to prove that this set is not countable. So for contradiction, we suppose it is countable. Since it is countable, we have a bijective function between natural number and our A. Then our A would be the set of F1, F2, F3, F4, da 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 da, because this is a bijection, okay? If you don't understand, I'm gonna tell you. F of 1 is gonna be a sequence of A's and B's. It's just we map the number 1 to such sequence. So F of 1 is a sequence. Let's just call it A, B, B, A, B, da 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 dot. So F of 1 is a sequence, F of 2 is a sequence. All of those elements are sequences of A's and B's. Now we define a new sequence that's called Z, and Z is Z1, Z2, Z3, and this is also a sequence of A's and B's. And we defined it as the following. So for each k in natural number, Z of k, this means the kth digit of Z, okay, the kth digit of Z. So for each k in natural number, Zk is A if the kth digit of Fk is B. And the kth digit of Z is B if the kth digit of Fk is A. In that case, we construct a new sequence that differs from all the sequence you can find in A. Okay? It's the same argument, okay? It's called Cantor's diagonal argument. It's the same thing as the proof of real numbers is uncountable, okay? Go over that proof. If you understand that proof, you should understand this proof, okay? Again, the kth digit of your sequence Z is A if the kth digit of Fk is B, and it's B if this is A. Then we find a new sequence that is different from all of the sequences in A, which means our F is not surjective, since then it's a contradiction, which means our A is not countable. Okay, let's continue. Now we have some definition. If A and B have the same cardinality, then there is a bijection from A to B. If A has, if this is true, which means there is an injection from A to B. If this is true, which means there is an injection from B to A. Now, the most important theorem here, Schroeder-Bernstein theorem. Actually, Cantor's name should be here as well. It's Cantor Schroeder-Bernstein theorem. Anyway, I like Cantor, that's why I added here. No, that's not why. Cantor's name should be there as well. Anyway, this theorem is saying that let A and B be two sets. If the cardinality of A is smaller than or equal to B, and the cardinality of A is greater than or equal to B, then the cardinality of A and B are the same. Well, this theorem sounds trivial, but the proof is not trivial. The proof is really long, and you don't need to know that, okay? This theorem is what you actually need to know. In other words, if there are injections F from A to B and G from B to A, then there is a bijection, H from A to B. With this theorem, a lot of questions can be much easier than before, because before we can only build a bijection from one set to another, and sometimes finding a bijection is really hard. But if you just need an injection, it's gonna be much easier. Here is an example. We want to show the cardinality of those two intervals are the same. Well, if you just look at those two intervals and you want to build a bijection, it's kind of hard. We'll still do that later. That's another technique I'll introduce later, but for now, we'll just use this theorem. So we need, first of all, we need an injection from either side, and I picked the easier side first because 0, 1, this is a subset of this, okay? Which means you can just use the identity function, and it's clearly injective. That is why this is true, okay? And I wrote down here, this is generally true if A is a subset of B, then the cardinality of A is less than or equal to B. This is generally true. How do you prove that? You literally just use the identity function. Map, so f of x equals to x. Okay, if you use this, it's in an injective function, then you can show this is true. Okay? This is the easy side. The other side is not hard as well, but relatively harder than the first side. So we consider another function g that maps from the bigger one to the smaller one, and we defined by this. How did I come up with this function? Again, I like number line, so we'll draw 1, 0, 1. This is my original interval, okay? And I want this to be an injective function. Remember, I don't need a bijective function now. I just need an injective function. So I want to exclude 0 and still map to 1. I want map this to this, and I want it to be injective. So first of all, I shrinked it. Okay, so first of all, I shrinked it by 2. Which means right now, my new interval looks like this. Okay? Now it's still not an injective function because you're 0. Okay, you have 0 here, you don't have 0 here. That is why I'm gonna shift this whole thing. I'm gonna put this interval in the middle. Okay, that's why I added 1/4. So this is 1/2, 1/4. If I have 1/4, I literally shift this interval to the middle such that if I map this to this, it's gonna be an injection. Okay, please think about it yourself. Just watching me doing this cannot get you anything. Please, please, please think about the whole question and do it yourself when you are free. Okay? Okay, finally we're at the fun part. Okay, not fun part. Again, as I said, this question, number 2 and number 3, are beyond the scope of this course. You don't need to understand those 2 questions. I'm introducing them because, well, some of you likes challenging questions. Well, the question's not really challenging. Oh, if for your information, those 2 questions were my assignment questions. It's second year course at St. George. The code is math 246. Okay, so when I took this course, those 2 questions were my assignment questions. Well, you can see I just copy paste my solution from my assignment. First of all, we want to show the cardinality of a unit cube is the same with a real number. Unit cube, well, in this case, I'm really bad at drawing this, but I'll still draw it. So if this is our x, this is our y, this is our z, our unit cube looks like... Okay, I think I'm really bad at this, but just draw a cube. Should not be hard. Okay, here we go. Unit cube right here. Okay, so I want to show the cardinality of this whole thing is the same with real number. Well, I used the theorem here. As you can see, I said to show this is true, we need to show 1 and 2. Okay, I'm gonna skip 1, it's an easy one, but you can read this if you have time. I'm showing you the proof of this question because I want to show you this. 2. Okay, let's only look at 2. So what I said, for 2 I want to show the cardinality of this unit cube is smaller than or equal to the cardinality of real number. So what I did is I want to represent the coordinates of points in this unit cube as infinite decimals. Why is that? Because the numbers from 0 to 1, you can always write all the numbers in this interval as 0 point something something. Okay, for example, 0.1, you can write it as 0.1000000, and 0.12222, like those. Okay, so all the numbers in this interval, you can write it as infinite decimals. Okay, I think that makes sense. And the second sentence I wrote here is, in ambiguous cases where a representation of a number could end in either a string of zeros or string of nines, we choose the representation ending in a string of nines. What I mean by this sentence, what I mean by this is that I hope you know that 0.99999 equals to 1. And yeah, that's what I wanted to say. Okay, so 0.99999 will equal to 1. Oh, wait, yes. So we can represent 1 in 2 different representations. And well, 1 is 1.0000000, like this. So the same number, we can have 2 different representations. And I'm telling you, if we have this ambiguous cases, we're gonna choose this one. Okay, so we are not gonna use this. Instead, we use this. Okay, I feel like some of you might not know this is true. Well, if you're interested of the proof of 0.99999 equals to 1, email me or think about it yourself. It's a really short proof. I'm pretty sure some of you can prove it yourself, but it's true. Okay, just believe me now. For now, if you're interested, email me. Anyway, that's what I mean. If we have this ambiguous case, we choose the strings end with nice. Now we have this function g from S2. S201, S is our cube here. Okay, so I'm gonna define this function as this. What does this mean? Well, this is my x, this is my y, this is my z. Okay, so each of my x, y, z, I can write it as 0 point infinite digits. Okay, as I just explained here. So I can write my x as 0.A1, A2, A3, blah dot dot dot, y as 0.B1, B2, B3 dot 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 dot, and z as 0.C1, C2, C3 dot 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 dot. Then my image of this would be 0.A1, B1, C1, A2, B2, C2, A3, B3, C3, and like that. Okay, this I'm claiming that this is injective and the others are not important for you. I'm showing you this because one, I want to show you how powerful is the theorem. The second, I want to show you a lot of times when you deal with uncountable, not uncountable, when you deal with a cardinality that is the same as real number, you should always think about the interval 0, 1. Okay, this interval is really useful sometimes, because in real numbers is really hard to deal with, but 0, 1 is much easier to deal with. You know that they have the same cardinality. Okay, so if another set that has the same cardinality with this implies it has the same cardinality with real number. And the reason I'm telling you this interval is really useful because all the numbers in this interval can be written as 0 point dot 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 dot, like infinite decimals, and that can make our life much easier. Again, this is beyond the scope of this course. You don't need to know this. If you don't understand, that's totally okay. Okay, just skip this part. The question 3, I want to talk about this because there is one thing I want to talk about. Okay, let's read the question first. Suppose we have two sets S and T. Both of them have the same cardinality with a real number, and I want you to show that the union of those two sets is real number as well. One thing I want to talk about is when you prove this, you cannot just build injection. Okay, you cannot do that. Instead, you want to write it as the union of two disjoint sets. Because if they are not disjoint, something's gonna go wrong. Okay, something is gonna go wrong. I'm not telling you why, but you should think about what's gonna go wrong. Okay, this is the main reason I want to talk about this question, because I want to show you that S union T can be written as this, which, well, in this case, S and T minus S are disjoint. Okay, so we have two disjoint sets, S and T minus S. Again, this shows you how powerful the theorem itself is. Let me see if anything's important. For those who are interested in this proof, see here, you might not understand this. C is just the cardinality of real number. Some of you might know that the cardinality of natural number is aleph 0. I think this is how you write it. And the cardinality of real number is C. If you are interested, this is beyond the scope of this course, as I mentioned. Other than that, I don't have anything else to talk about for this. Okay, the last proof technique I want to talk about, I call this hotel. And I only have one example for this. I think this might be a little bit too hard for 102, but I'm not sure because, well, I'm not sure. Anyway, I want to talk about this. Again, you don't have to know this, but you know, why not just learn more material, right? Yeah. Anyway, in this case, I want to build a bijection directly from this interval to this interval. Well, we showed that those two intervals have the same cardinality before, use the theorem. So we built two injections. In this case, I want you to build one function, like one bijective function, which is gonna be much harder than before, but still we can do it. And this technique, I'm gonna explain it to you on this side, okay? So on this side, this is my explanation of my hotel technique. So consider this. Day one, we have a hotel. Day one. Okay, so the story is that you own a hotel and you have infinitely number of rooms. Okay? You have infinitely number of rooms. You have a huge hotel, infinitely large. And day one, you have infinitely many of customers. Okay? Now I'm telling you our x. So you know function is like you have x to f of x, right? You map from your x to f of x. So I'm telling you that your x will be your customer, and f of x will be the room number. Okay, the room number of each room. Day one, each customer is gonna live in the room number that matches with their name. So the first customer, his name is 1. He's gonna live in the room 1. Okay? The customer 2 is gonna live in the room 2. Oh, actually no, it's between 0 to 1. Okay, it's only between 0 to 1. So customer 0.001 is gonna live in 0.001, just like that. Okay, so customer is gonna live in the room that matches with their name. That's day one. Okay, well, your f of x is gonna be this. Just gonna write here 0, 1. Okay, now day 2, another customer moves in because, okay, as you can see, this interval and this interval, the only difference is that this has 0. This includes 0, the second one does not include 0. So your day 2, you have another customer moves in. His name is 0. So 0 moves in and he wants to fit in your hotel. Well, intuitively, you would think, well, oh, we cannot fit because, well, before 0 comes in, each one of your customers living in their own bedroom, and it's a bijective function, okay? But since you have infinitely many bedrooms, you can actually make it work. How do you make it work? U0 is gonna kick 1 out. So literally we are just looking at a sequence. We are looking at a sequence in 0, 1. And this sequence I'm looking at is 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on. Okay, I'm only looking at this sequence. Everyone else stays in their own room. I'm only looking at this sequence. So for this sequence, 0 is gonna kick 1 out. 0 is like, okay, move. I'm gonna live in your bedroom. Okay, so 0 moves in bedroom 1. The 1 is homeless. 1's gonna be like, okay, I need my own room as well. So 1 kicks out 1 over 2. So 1's gonna live in 1 over 2. 1 over 2 is gonna live in 1 over 3. 1 over 3 is gonna live in 1 over 4. And so on. Okay? Everyone else stays in their own room. It's just those customers, you don't like them, you want them to switch rooms so that 0 can fit in. Okay? This is how we build our function. This is a formal function. So if your x is 0, which is here, if your x is 0, your y is 1. If your x is in the form of 1 over n, where n is natural number, they live in 1 over n plus 1. So same here, 1 over 1 is going to live in 1 over 2, 1 over 2 is going to live in 1 over 3, and so on. And everyone else stays in their own room. I call this hotel because I think it's kind of visualized. I don't know if it's helpful, but it was helpful for me when I took the course. Anyway, I think it's a little bit harder than 102 material, but well, it's fun. I think it's fun. Anyway, the last example, this question, I think it's a good question. But I'm not gonna cover it today. I will do this question tomorrow with some other questions that relating to Euclidean algorithm and fundamental theory of arithmetic and stuff. So I will make another short, I promise it's gonna be short. I'll make another short video tomorrow. And that might be my last video of this semester, or I don't know, probably my last video. Good luck everyone. I hope you do well in 102. Have some rest, don't stress out too much. Anyway, bye.